Okay, today I'm going to go through this Pearson Edexcel linear physics exam for A-level Advanced Physics 2. Now this is equivalent in content for year 13 to the IAL students doing their Unit 5. Okay, so the theory covers Unit 5. So year 13, Unit 5. IAL, but it also includes waves and materials from year 12. So year 12 is 2 topics and year 13 is the same content as IAL Unit 5. So the style of the questions is slightly different. So you can use these for if you've done all your IAL papers, you want to have a look at some more questions, you can. So I'm doing this old paper because my students are doing some practice papers over the spring break, and this is one of the ones that I've asked them to do. Okay, so I'm just going to go through it and then allow it to stay on the YouTube for future students to also benefit from. Okay, so the multiple choice is the same as IAL. They start with 10 multiple choice questions. The length of the exam is the same. Which of the following wave properties is not exhibited by sound waves? The sound waves are longitudinal, and longitudinal waves cannot be polarized. Question 2, 2 springs are sharing this load because basically the 20 newtons is split between them. And there's 8 centimeters extension. So it's as if you got 10 newtons for the extension per spring. So the stiffness constant can be worked out for each spring as 1.25 newtons per centimeter. It then says if you apply a force of 5 newtons to one of the springs, and we've just worked out the K for one of the springs by dividing the force by 2, dividing that by the extension, given there, and you can then work out what will 5 newtons do with the same stiffness constant spring. It will create an extension of 4 centimeters. Okay. Question 3. A swing completes 24 oscillations in 1 minute. So the frequency is 24 over 60, which is 4 over 10. Yeah. So that's going to give you B as the answer. Okay. Question 4. Which of the following is not a similarity between gravity and gravitational fields and electric fields? So I've ticked the first 3, so they are similarities. They all obey the inverse square law. For a point charge, it's always radial. That means going out like as spokes on the bicycle wheel. And they can act at a distance because they are fields. But not both fields act on all particles. Now, all particles have mass, yes, all particles have mass, but not all particles have charge. So gravity acts on all particles, but electric fields only act on particles with charge. So D, it's not true that both fields act on all particles. Question 5, a data book contains information on latent heat of fusion, which is a change of state between solid and liquid in either direction, and the latent heat of vaporization. So it also can be used for condensation. Okay. So if you vaporize something, you go in an opposite direction, you're condensing it. Okay, so 545 joules is transferred from ethanol when it condenses. Okay, so when it condenses, it's making bonds. So we need to use this value. And the equation is E equal ml. And they want you to calculate the mass. So if that's the energy per kilogram, then you can work out how much mass will condense using 838 kilojoules per kilogram. So you want to divide 838,000 by no, you want to divide the energy, 545 on top, divided by 838,000, so that's B. Okay, question, so here's the first 4, and the question 5 is on the next page, so I've put them in. So you can see over here we got 2 questions from year 13, content, and 2 questions from year 12. Okay? So that's the difference between a linear and a modular. Here you have a question from the on a Hertzsprung-Russell diagram, so from year 13 astrophysics, and they just want you to know which region you'll find the sun in. Well, the sun will be around here because this is the luminosity of the sun. Yes, the luminosity is given relative to the sun. That symbol there means the luminosity relative to the sun. So you want to go across there, and the sun's temperature is about 6,000 Kelvin. So where those 2 lines cross is where you should find the sun. So B is the correct answer because B is main sequence. Okay? Those are the 2 values that you should really know. Yeah. And of course, just to know the others, A is a white dwarf star, D and C are giant stars, red giants. And then a black body radiator of temperature T and surface area A has a luminosity which can be calculated using this equation, which is the Stefan-Boltzmann equation, which is on your formula sheet. Which of the following is the luminosity of a black body radiator with a surface area of A over 2? Okay, so if this A is given for the first luminosity, if we divide the area by 2 and multiply by temperature by 2, you'll notice that the temperature is to the power of 4. So you can just put double T to the power of 4 and A over 2 outside, and you'll get the variation in luminosity compared to before. So then you'll see that is T to the 4. This is all the same as the normal luminosity. So the difference is 2 to the 4 divided by 2. So it's the original luminosity times 2 cubed. So it'll be 8 times the luminosity original. That's D. And there we go, B, B, and D for the last 3 questions we just went through. And here you got a line spectra in hydrogen in the Milky Way galaxy. So it's from a star in the Milky Way galaxy observed to have a shifted wavelength of 656.3 nanometers. In a laboratory on Earth, so when it's stationary, I call that lambda naught, will be 654.9 nanometers. So you can see it's increased, so it means it's redshifted. But they want you to work out the magnitude of the velocity of this star. So we know it's moving away from us because the wavelength has gone towards longer. Okay, but to change the velocity, you've got these 2 equations, same as in GCSE. The difference in the wavelength compared to the original or the stationary one, which I've called lambda naught, is the same ratio as the velocity compared to the speed of light. So you can just use a bit of algebra. You know delta lambda there. You know the original lambda, as in if it was stationary. You know the speed of light. Put the values in, and looks like a 656 minus 654. So the only one that's got that on top is this one, and everything else looks correct. So it should be D. Number 9, an object is placed at a distance U from a lens. Focal length is given, and the image is formed 9.8 centimeters. They just want you to work out the magnification, which is 9.8 V divided by U divided by 6.5, which is about 1.5. C. Question 10, you have diffraction grating. There's the equation for diffraction grating. They've shown you the central maximum and the first order maxima on each side, and they want you to work out which of the following would cause the first order maxima to be closer to the central one. Okay, so in other words, we want theta to go down in the equation. Moving the laser closer to the grating makes no effect. Moving the screen further away will just spread out the distance, so that will get further, but we want to go closer. Using a diffraction grating with more lines per millimeter means that the D will go down, yes, and in the n lambda equal d sine theta. If D goes down, that means they're inversely proportional because they're on the same side of the equation. Sine theta will go up, so it's wrong. So the answer must be, if you change the frequency to a higher frequency, the wavelength goes down, and the wavelength is directly proportional to sine theta, which means theta will go down. So the answer is D. Okay? So that's the multiple choice done. Yeah, and there's the mark scheme. So you can stop the video if you wish to. Okay. Question 11 is now the structured questions. So in the IAL, they call this section B. Over here, they don't differentiate. An electric iron rated at a power of 2,600 watts contains a steel plate which is heated to a temperature of 215. Room temperature was 18, so you know you're talking about change in temperature, so it's specific heat capacity. They're given the mass of the plate, yeah, and they're giving you specific capacity of the steel. So we know C, we know the temperature change. Can this power reach this working temperature in less than 1 minute? So they want you to find T, where the power times time is the energy that goes into the heating plate, steel plate. So you just put all the values in and put T as the subject, and you'll get 30 seconds. So yes, it can reach it in less than 1 minute. 3 marks. So this is a paper I went through with some of my students online because we were working from home due to the current situation in the Middle East. Okay, so there's the mark scheme if you want to have a look at your own answer and see if they have any alternatives. So here, for example, there are different ways, they're saying, of solving it. Okay. The next question is about two black holes orbiting each other. Yeah, so they're kind of orbiting the center of their masses, which is in between them. That means A must be more massive than B because C is closer to it. So the center of the mass of the system is the center of the circular orbit for each of them as shown. So a black hole has an orbital radius given, BA, and black hole B is also given. Both orbit with the same period. That means 6 months later, B will be here, yeah, and A will be there. So what does that tell us? So the total distance between them doesn't change, and it's been given. So you want to calculate the force between them, you use Newton's law of gravitation. Okay, so we know the two mass values, we know G is a constant, it's on your data sheet. So one is 36 times the solar mass and one is 29 times. So I just multiplied those two numbers and that squared the mass of the sun, which is also given to us here, and divided by the separation which stays constant between them. Okay? So basically at opposite sides each time, which makes it possible for you to use that equation, and you get, put all the numbers in to two significant figures is all you need to give it to. Because they've only told us data given to two significant figures above. Okay. Then it says by considering one black hole, yeah, you can determine the period of that orbit. Well, basically it's centripetal force, so you're using further maths. So you know mv squared over r must be equal to the force that we just calculated above. And you know v is, from GCSE, is 2 pi r over t for circular orbits. Okay. Remember, physics is the simplification of reality. So I know no orbit is 100% circular. So this allows you to do the algebra, and if you can follow it, you'll get to a value for t squared, which I have done in 3 steps by putting v into this equation and equating the force with Yeah, basically I've just done some algebra. Okay, so when you put all the values in, make sure you don't make any mistakes. You get a mark for putting all the correct values in. Yeah, and I've worked out t squared, and then I don't forget to square root it. And I've given the answer to two significant figures. Okay, the mark scheme will show you how they are allocating the marks for each part. I'll let you stop the video if you wish to have a longer look at it, because you can also use omega squared r instead of v squared over r. Now this is a really common question, so you've got to get used to this. The next question is about working out the distance to nearby astronomical objects, nearby relatively in astronomical terms. So we can use the trigonometric parallax method, which is looking at the star against the background stars which are further away, and work 6 months apart, so from two sides of the sun, and work out how much is shifted against the background stars. Okay. For objects beyond a certain distances, we have to then use a different method called standard candles. And the first question is, what is meant by a standard candle? It means an object, stellar object, with a known luminosity. Certain stellar objects have got constant velocities, like Cepheid variables, and certain types of supernovae events. Okay, and that allows us to use the luminosity and intensity equation to work out roughly how far away they are. Explain why the trigonometric parallax is not used beyond a certain distance. Well, the problem is because we need to measure the parallax angle 6 months apart on each side of the sun. The angle becomes too small for very distant objects. Okay, it's too small to measure, or it also, the percentage, at smaller and smaller angles, the instrument resolution is obviously a certain value, and for very large distances you're going to get very large percentage uncertainties in your data, so it becomes invalid. Okay, so you can only measure up to a certain degree of arc seconds. Okay, describe how distances too large for both these methods, standard candles even, can be determined. Well, then you need to look at the shift in the frequency that we looked at before in an earlier question. So for example, look at the redshift, and from that you can work out the velocity like we did before, and from that you can then use the Hubble relationship, which shows that the recession velocity of distant galaxies is proportional to their distance from us, and that allows you, because we know h0, to determine the distance for objects which are further away. Okay. Once again, here's the mark scheme. They haven't given any additional guidance, so you can have a look. Question 14. Here you have nuclear fusion involving small nuclei. So small nuclei, that'll be fusion goes up. Fusion is this way. If you're going higher in this value, you're basically releasing energy. And fission is when you split larger nuclei into smaller ones. And if you're going that way, you're also going up the binding energy per nucleon curve, so they both release energy. Okay? So they both release energy. Okay? Because of the mass deficit. So using this curve, explain how both fusion and fission release energy. So that the energy per nucleon curve peaks at a certain value, which is iron 56. And for iron, is the maximum binding energy per nucleon of any nucleus. So moving either way towards this peak leads to an increase in nuclear stability, is what I'm saying, which is an increase in binding energy per nucleon. So increase in binding energy per nucleon of any nucleus means that it's more stable. And when something is more stable, it's held more tightly together. And it's kind of like the ability to release energy, a bit like an exothermic chemical reaction. This releases energy, And this releases energy by the equation due to Einstein's equation of mc squared, where the delta m is how much mass is released in the process. Okay, so in nuclear reactions, mass is not constant like in chemistry. So fusion of smaller nuclei leads to an increase in binding energy per nucleon because we release some mass. Yeah, so you get some mass released. And same with fission of larger nuclei. When you look at the mass before and after, you also got some release in M. Okay, so both the mass will decrease in both cases. So when you look at the mass before, when say fission, and it produces like uranium is a kind of one that we've looked at in GCSE. When it splits up into smaller daughter nuclei, if you look at the masses before and after, they don't add up, yeah, to say 5 decimal places. And the mass decreases, and that mass decrease leads to this release of energy using E equals mc squared, okay? And when you divide it by the number of nuclei, the peak occurs at iron. And by dividing it by the number of nuclei, it's a way of comparing the stability of nuclei. Okay, so the nucleus with the highest value of released energy divided by the number of nucleons is iron. In both cases, mass deficit is observed, yeah, as in decrease in mass is observed, I should say. Mass is reduced and energy is released by this equation. Now, hopefully that will get you all the marks. I hope I've explained it clearly. Explain why the conditions required, A, to bring about nuclear fusion, and B, to maintain nuclear fusion. So to bring about nuclear fusion, gravity gradually coalesces protostars, mass of gas like a nebula, and gradually over millions of years it becomes much higher in density, which then also obviously by collision theory, yeah, the kinetic theory of gases, produces higher pressures due to them being in closer proximity. You get a higher rate of collisions, yeah, and the higher pressures using the kinetic theory leads to higher temperatures, and at very high temperatures you have very high kinetic energies. And you need very high kinetic energies to overcome the electrostatic repulsion, yeah, between protons and protons, which nuclei have. Now, 75% of the original nuclei formed in the universe after the Big Bang, 75% was hydrogen, 25% was helium, and that happened before the formation of any stars. So you need high kinetic energy, so you need a density of plasma, if you like, high temperature gas, to overcome the repulsion which protons will feel for each other. At these high temperatures, nucleons can fuse together and release energy using the same process I just explained. Yeah? And in the process, that release of energy also increases the kinetic energy, which maintains the nuclear reactions. So if you have more kinetic energy coming in, basically you get higher pressures, density increases, and the rate of collisions can be maintained, needed to keep the nuclear fusion process going. Okay, so I hope those 3 arrows between them get everything that's on the mark scheme, which I'll allow you to have a look at in your own time. Okay, all right, so straight ahead. The reason I'm going through this fast is because the students who asked me to go through this have already been through it with me, okay? And the students who haven't been through it with me can look at this. I'm sure there are alternatives to this on the internet, but I think mine are slightly different in that I explain the physics behind it in more detail. I'm not just solving the problem to get views, okay? The figure shows apparatus using 2 Polaroid filters. Okay, right now they're both oriented in the vertical plane direction. So the light that's vibrating in this plane, up and down, will get through both filters. But light going at right angles to that, the components of light going at right angles to the filter orientation will not get through. So only at this stage, only 50% of the original light will get to the detector. The arrows shows the orientation, as I explained, of the filters. Yeah? Light incident on filter 1 and light incident on... and the intensity of light is measured using the detector when the filters are in the positions shown. So we're going to get 50%. Filter 2 is then rotated relative to filter 1. The intensity of light is then measured for different angles of rotation. And you can see from the graph that as you go from 0 degrees to each other, so when filter 2 is in the same orientation, you'll get the 50% of light getting through. But when you get at 90 degrees, it will decrease to 0, because at 90 degrees, they're exactly perpendicular to each other. And that means the first filter only lets vertically polarized light components go through. And at 90 degrees, the second filter will block all vertical components. So you're going to end up with 0 intensity at 90 degrees. As you change the angle back towards 180 degrees, you'll gradually go back up to the 50% intensity. And at 180 degrees, they're back in the same orientation as each other. So that's basically what they want you to answer in the next section looking at this graph. Okay? So explain the effect of the filters on the intensity of light. And it's a 6-mark question. I think it's a generous 6 marks. Original light must be unpolarized. Yeah. That means unpolarized means that the oscillations are in all planes or in all 360-degree directions. Okay. Filter 1 only allows vertical oscillations to pass through. So you're going to get 50% intensity of the original intensity of the light. All horizontal components of the light are thus absorbed by filter 1. As the two extremes of the graph, 0 degrees and 180, the two filters, I've said, are both in the vertical orientation direction. No further loss of intensity occurs at these points. Yeah? Okay, but at 90 degrees, the second filter is at right angles to the plane of polarization of filter 1. Because basically these Polaroid filters are crystalline structures which only allow the light to get through if it's going in between the planes of the crystal. Okay? So all the light will be absorbed at 90 degrees. Okay? In between 0 and 90 and 90 and 180, the second filter is rotated. Therefore, only a component of the vertically polarized light coming through filter 1 can get through filter 2. So the intensity varies from 50% to 0, which is I naught over 2 is 50%, then rises again from 0 back up to the maximum intensity divided by 2, the I naught being the intensity of the original bulb. And those 6 bullet points should get you the 6 marks. And here, it's not just what you've said, but how clearly you have said it. Okay? So you've got to show, your answer has to be structured and show clear lines of reasoning. So you get 4 marks for mentioning all the points that I mentioned, and then they give you up to 2 if it shows if your way you've written it, your answer shows a coherent and logical structure with linkages and fully sustained lines of reasoning throughout. That means you don't confuse the examiner. Okay? Very common to have one of these in each question. So here we have what's called a Cartesian diver, which is some air trapped in a container that's inside water. So here we got water, and inside the top of this pipette, there's some air. Yeah? Yeah? So the air that's trapped creates an upward force, upthrust. Okay? So the diver is made from a plastic pipette in this case. Yeah, there's different shapes. So when placed in a plastic bottle full of water, the diver because of upthrust, rises and touches the top of the lid. So now the lid will stop it keeping on going up. So the upthrust gets to the top, and the lid at the top produces a downward force along with the weight of the pipette, the Cartesian diver, and you get a balance point when it hits the lid. Show that the downward force due to the lid is about 0.02. So this is what you've got to show. To one significant figure is at about 0.02. So they want to see if you can work out everything. They give you this data, yeah, so the volume of the diver, yeah, and the mass of the diver, and obviously you know G, so you can work out the weight. So that's the downward force due to the diver's weight. And then they're giving you the density of water, which is 1,000 kilograms per meter cubed. Now you know the upthrust is always equal to the weight of the water displaced. And we know that the volume is given of the diver. Well, that displaces its own volume of water. And we know the density of water. So you multiply that by gravity, volume, times the density, times G gives you the upthrust. So we know that looking at my force diagram above, that the force on the lid plus the weight must equal upthrust. So the force on the lid, yeah, will become the upthrust minus the weight. So you take away the two values I've worked out above, and you get 0.0206 to 3 significant figures, which I said you've got to put to 1 significant figures, because that's what they've asked you to do in the show that. So show that questions means you've got to prove it mathematically. All right, then it says, when the pressure is increased by squeezing the bottle, so the man is squeezing the bottle, that forces some water into the where the air was. Remember that inside there we got an air pocket. But by squeezing the bottle, the increase in pressure will squeeze the air as well, and water will take place. So the air volume at the top will decrease. Okay? So, water is forced into the diver, or the air pocket, which increases its weight. I suppose that's true, but I'm saying, or decreases the upthrust due to the lower volume of the air pocket. Okay? So there'll be a lower volume of air pocket because the V decreases. And that's what they want us to calculate. So we still, the diver sinks, but then reaches a balance point. So it kind of hovers halfway down the water. So at that point, the upthrust must equal the weight, the original weight. Yeah, the reduced upthrust due to the air being squashed. That's the way that I think is the best way of doing it. So the volume of the air that they gave us in the first part hasn't changed. Yeah, they gave us the volume. And we want to show that the new volume of air has gone down to about 3/4. So this is what we want to show. Remember, we've got to prove it mathematically. So if the balance forces, the new upthrust, which is the way I'm doing it, must equal the weight from part A. So I don't think the weight of the pipette itself has changed. Is what happens. The air pocket inside has been squashed. So I'm saying there's a new upthrust, not a new weight. Okay, and the new upthrust is rho V dash, which is what I want to calculate. Rho hasn't changed, it's still water, yeah? And G hasn't changed, and the weight from before hasn't changed. So I think this is the correct way of doing it, the best way of doing it. So when you do that, you'll see the volume is 5.92 times 10 to the minus 6, which to 1 significant figures is what they want us to show. Okay, so always give more significant figures to show that you know that you've got to then round it to the correct number of significant figures for the final answer. Okay? So the pressure of air in the empty pipette in part A was this much. So we know pressure at 1. They want you to calculate the pressure of the squashed air. Well, it's going to become 3/4, surely. So it's going to be squashed to 3/4 of the volume. So the pressure will increase by an 8 to 6 ratio but I put the accurate value, yeah? And it's basically PV is a constant because PV equals NKT. So you can just use your GCSE knowledge and you'll see, if you can follow my method to two significant figures, it should go up to 1.4 times 10 to the 5 pascals. Here's the mark scheme, and they did it their way, and I'm saying mine is a clearer method. So this is what I did. I did the OR method, and that's what I would recommend. Okay, so that's question 16. And here we have a Coulomb meter, which you may or may not have seen. It's used to measure charge, and you can see here it's got a value of minus 226 nanocoulombs. So, and then on the top, I think they put zinc here. Okay, so they put a zinc plate there. Let's draw that again. So they put the zinc plate on top, and they're going to demonstrate the photoelectric effect using zinc, which is common. So the zinc was given a negative charge. So the zinc's charge is 26 nanocoulombs, which is negative. Okay. So how did it happen? Under normal lighting conditions, the charge remains constant. So normal lighting conditions like daylight, so mostly visible light. When the zinc was illuminated with an ultraviolet light, the magnitude of the charge on the zinc decreased because you're releasing electrons, photoelectric effect. So ultraviolet has a greater threshold frequency than visible light. When a larger sheet of zinc was then used in the second part of the experiment, the charge on the zinc decreased more rapidly. Okay? If the area increased, you're going to get more photons arriving per second. So that's what you've got to explain. In each case, the initial charge on the zinc was the same amount. So they controlled, that's the control variable. They haven't necessarily said how they charged the zinc. Doesn't matter. Okay? I'll let you think about that in your own time. So explain these observations. So normal light frequency is below the threshold frequency needed for zinc, for photon energy to be high enough to release electrons. Remember, that photon energy is calculated by E equals HF. Yeah? But photon energy must be greater than the minimum energy, which is called the work function for each metal. And that's the energy required to get an electron to the surface of the metal. Yeah, to just emit an electron, to free it from the structures of the zinc lattice structure. UV light has a higher frequency and therefore higher energy than normal light. Yeah, so it has a frequency greater than the threshold frequency for zinc. Yeah, needed to give sufficient energy to release an electron. Yeah, this is the equation. HF is greater than phi, and phi is what we call the work function. So it's good to put your equations in brackets to show that you know the maths involved. Remember, each photon gives its entire energy quantum to one electron. One photon, one electron. You always need to include this in your model answers. When a larger area of zinc was used, you basically have more photons incident on the plate in a given time. So there's more photons hitting the zinc, and therefore, because it's one electron per photon, you're going to get a faster rate of emitting electrons. So more electrons gain the required energy, yeah? In the same time, you're going to get more photons, so you're going to get more electrons. So the charge will be lost as more electrons are leaving the plate per unit time. Okay, hope that makes sense. Here again is another 6 marker, which remember, you need to say what I've said in a coherent, logical, fully sustained lines of reasoning manner. And here are the points they're looking for in your content. Okay, Now, my answers are more detailed because I'm trying to teach you this if you've missed it in your own lessons. Here you got, for one sheet of zinc, how the charge at different times is measured. So it's charge against time, and I was saying it looks a bit like a capacitor discharge curve. Okay, so if you drew a curve of best fit through it, you'll get something like that. Students suggest that this is an exponential decay curve. Well, if that's true, it should follow this rule, where Q should equal to Q naught e to the minus a constant multiplied by time. Yes, if it's exponential, that must be followed. So if you plot this graph, if you take the values and plot it as ln Q against time, and if it is exponential, you should get a straight line graph, which would have a negative gradient. So basically will look like this. Well, that will be the initial charge value. So you do ln Q there, T over there, and you can work out the gradient will be equal to the constant of proportionality between ln Q and T, okay, using the y equals mx plus c format. Okay, that's how you know. Or you could take values from this and see if it's like halves every so often. That would also be like the GCSE method. So you take the initial charge and see when it goes down to half, then see when it goes down to quarter, and see if you can show that it is obeying the old half-life rule. Okay, that's question 17. Okay, some guidance notes there for your own answers. And question 18 is a eye. So eye has a cornea and a lens, which hopefully focuses the image on the retina, unless you have poor eyesight like me. It is suggested that the cornea provides 80% of the focusing power of the eye. So I call that the power of the cornea. Determine whether this is correct. They've given us the values for focal length of the cornea. So that should be in meters normally. Focal length of the lens has also been given. So you can see that the focal length of the cornea is shorter, so it's more powerful. Okay? Because power is 1 over the focal length of each lens. So you can work out the power of the cornea as 44.84 by doing 1 over its focal length. Do the same for the lens, and you can see that it's higher. But is it 80% of the total? The total, then you add them up and work out if this to that is 80. And if you do that as a percentage, you'll see that it's 71%. So it's less than 80%. So the suggestion is not correct. Part B, the light from a point object forms a focused image on the retina. The cornea and lens may be treated as a single item, yes, with a focal length of 1.6 centimeters. That will give you the equivalent power of both, which we worked out on the page before. So here, and the retina, the distance from the retina is 2.4 centimeters. That's just the shape of the eye. Calculate the distance from the point object to this single lens when a focused image is formed on the retina. So we know that V should be 2.4, and we want to work out U. So U will be 1 over F minus 1 over V. And you get this, reverse it, you get 4.8 centimeters. Okay, and then a ray of light strikes the front of the cornea at an angle of 15 degrees, so that's the refraction we're talking about. Calculate the angle of the ray in the cornea, so it's now gone into the optically denser, so you've got to find R or theta 2. They've given us the speed of light in air and the speed of light in the cornea. So from these two velocities, you can work out the refractive index of the cornea, which I've done to 3 decimal places, 4 significant figures. You can then use this equation with n1 equals, for air is 1.00, and we know these already from above. So you can just work out sine theta 2 by using the equation and you'll get theta 2 being 10.84 degrees to 4 significant figures, but you really can only quote it to the nearest degree because that's what they gave you the original angle at. Okay, so people swimming underwater often wear goggles, yeah, or if you go diving, you wear goggles. Goggles enables them to see objects underwater clearly, whereas without goggles, things appear blurred because it's going from water into cornea rather than from air into cornea. So the refraction will differ based on the relative refractive indices of the two materials. Air to cornea, higher difference in refractive indices. Water to cornea, similar refractive indices. So you see the speed of light in water is 2.25 times 10 to the 8 meters per second. Let's have a look at what it was here. You see the speed of light in the cornea was very similar, 2.2 to 1 decimal place, and here is 2.25, so 2.18 to 2.25. So it's not much difference. So it's not going to refract much when it goes from water into the cornea, and that makes it more difficult for your eyes to adjust. So when you wear goggles, the eye is in contact with air rather than water, H2O I put. So the difference in the refractive indices and speeds from air to cornea is much greater than the difference if you just try to look at an object underwater through water. Okay, so more refraction will occur from air to cornea compared to water to cornea. So this makes it easier to focus on the objects. Basically, you have more power in the cornea if it's coming through air first. Yeah, so the power of cornea with goggles is the power to bend light. The refraction increases, so the power increases. Okay, so that's how you've got to explain it. A good question for you to practice before your real exam. Okay, so there's the mark scheme. Again, let you stop the video if you wish to take a deeper look. Don't forget, if you find these videos useful, please share them with anyone else you think is doing a similar exam to you. I'm really looking for more schools who do linear because most of the schools out where I am are doing modular, and most people who follow me, so my subscribers, are waiting for me to do more modular exams. So I need to get more students following who are doing linear exams. Okay, your help is appreciated. Like, share, and subscribe, please. Thank you. Okay, especially if you're my students. If you haven't liked my videos, why not? Okay. Are they that bad? So, a school science department keeps a piece of potassium chloride to test as a test source for Geiger Müller tubes. Okay, so it's radioactivity. Potassium contains 0.012% of the unstable isotope, which causes the beta decay. Okay, so they want you to do this. Work out the beta decay without having to worry about the neutrino. Okay, it's not particle physics. We're just doing balancing top numbers, balancing bottom numbers, and if you do that, you know one of the neutrons has changed into a proton and emitted an electron. So a teacher makes some measurements using the potassium chloride test source to determine whether the Geiger Müller tube is sufficiently efficient at detecting beta radiation. Okay? So are Geiger Müller tubes efficient at detecting all types of radiation? Well, the answer is no, they're not that efficient because not all the beta particles will get into the Geiger Müller tube to cause an ionization effect. The potassium chloride sample has a mass of 0.3 grams. Now remember, we know that 0.012% of it is radioactive, not all of it. Show that the number of nuclei of potassium-40 is about 3 times 10 to the 17 to one significant figure. So you've got to show that. So another mathematical proof. The number of nuclei in 1 gram of potassium chloride is that, and 0.012% of those. So I should really divide that. I should really write that as I didn't do that, so that should be times 10 to the minus 2. Will be the number that you get. So I think if you do that, you do get the right number. 10 to the 21, 10 to the 17, that will take it down to 2, and that will take it down 2 more. Yes, so that sounds right. So I've got it right now. Okay, so the answer is 2.9 times 10 to the 17, which is approximately what they asked us to show. Okay, to one significant figure. Okay. Now it says show that the activity of this sample is about 5 becquerels. Well, activity is lambda n. There's a negative sign in there. But if you just want the activity, there's a negative sign in there because it's a decreasing. The number is decreasing, so the gradient is negative. Okay. Activity means dN by dt for those of you who do differentiation. Half-life is given in years. Yeah. So you could work out the decay constant in years, and then when you convert it into seconds. I haven't shown the conversion, but this is taken from the examiner, so it will be correct. Okay? So that's the 3 significant figures. Once you got the decay constant from the half-life, which is common, that you need to do this in your A-level exams, multiply by the n, which we just worked out in part B1, you'll get that it's approximately 5.1, which is equal to 5 to 1 significant figure. Okay, so another show that question. Once we know it's 5.1, with no sample in front of the Geiger-Müller tube, we got a background level of about 15 counts per minute. When the potassium chloride sample is placed in front, you get 176 in 10 minutes. So the background is 115 per 10 minutes. So the difference is only 26 counts in 10 minutes. Okay? And a detector, like a Geiger-Müller tube, is considered to be efficient if it can detect 7.5% of the beta emissions. So we got to work out how much have we detected knowing the values they've given us here. Yeah? So how do we do it? Recorded count adjusted for background will give us only 26 in 10 minutes. That says 10 minutes. My writing, sorry. So that's 26 in 600 seconds, which is 0.43 becquerels. Well, that's as a percentage of the 5.1, which we worked out is what we've actually got. That's less than 1%. So it's not efficient. It's not considered efficient because it's less than 7.5 by a lot. It's less than 7.5% of the beta emissions that we calculated in part 2 above. So it's detecting less than 1%, so not efficient at all. So why does it not manage to do it efficiently? Okay, explain a possible reason such a low proportion are detected. Well, some of the beta particles could be absorbed before they actually enter the Geiger-Müller tube, including in the sample itself, because they may be coming from deeper inside the sample and get absorbed by other atoms in the way. And not all the beta particles are going towards the Geiger-Müller tube as they are emitted in all directions, and the Geiger-Müller tube is a narrow section of the 360 degrees where they will be emitted in. Okay? But they could also be absorbed by the Geiger-Müller tube's window, because obviously the window is made of something solid. So you're not going to get them all. And these 2 points will allow you to get the full marks for the mark scheme. Have a look at the mark scheme for yourself. Okay? So this is really for those people who didn't come to my revision session in last week. Okay? Doing another one on Tuesday. So please let me know if you would want to attend. The science department has also a sample of strontium-90, which has a much lower half-life of 29 years. Remember the other one was in 10 to the 9 years? So state-wide, the half-life of potassium-40, which is much higher, makes it, the potassium chloride, a more suitable material than strontium-90 for the test. Yeah? Okay? Because in my last school, we actually had the samples for like 3 decades, and obviously for a half-life of 29 years, then obviously the sample was not as active anymore. So the sample of potassium-40 has a half-life which is much greater than the strontium-90, which is given 29 years. It was 10 to the 9 years, billions of years versus 29 years. So its activities doesn't vary over time. So it makes it a more suitable material for the test that they were talking about in this question earlier. Okay? I'm trying to do this in one run-through, okay, which is not easy. Okay? There's the mark scheme. And here we got question 20, which is looking at a laser interferometer gravitational wave observatory, abbreviated to LIGO. Okay? So it announced that gravitational waves have been detected in 2016. Okay? Gravity is a very mysterious, unknown part of physics, not clearly understood. Okay? We understand some of its effects. Now here there's a mistake, there shouldn't be a 0 there, because you can see the 0 is the middle. The signal detected is shown in the graph, so it causes some kind of strain oscillation on something, on the interferometer. Okay? And you can work out how the period of these oscillations varies along the time axis. Okay? The gravitational waves are thought to travel at the speed of light. So assuming that, determine the mean wavelength of the waves. Okay? Detected between 0.30 and 0.35. So between here and here, you've kind of got 2 complete waves. So 2 complete waves in 0.05 seconds gives you a period of that, allows you to work out the frequency. So I get it to about 40 hertz. And because C equals F lambda, you can then work out the wavelength using the fact that they told us that it's traveling at the speed of light. So the wavelength will be about 7.5 million meters. Huge. Okay? So the gravitational waves alternately compress and stretch the matter by small amounts as they pass through. The LIGO detector has 2 arms at 90 degrees to each other as shown. And each side of the arm, because there's huge waves, are 4 kilometers across, 4,000 meters in each arm. As the gravitational wave passes through the detector, the arms change length, and depending on the orientation of the direction, say the waves are coming in from this way, then it will have a different effect on the 2 arms because they're at right angles to each other. Okay? The detector compares the length of the 2 arms looking for changes in the matter. Yeah? Compress and stretching. That's what they think. An article states that the maximum change in the 4 kilometer length is about 0.01 times the diameter of a proton. Well, that's not very big. That would be the diameter of a proton, the 0.01 of the diameter of a proton. They've given us that here. So I just thought I'd just calculate it for myself. Determine whether this statement applies. So we got to work out the delta length, a bit like a show that, for the waves shown in the graph that we just looked at. So the graph shows strain, and the maximum strain in the graph will be the maximum change in the length. The maximum strain is given on the graph I work out as 1.2 times 10 to the minus 21. Remember, strain doesn't have a unit. It's the ratio of delta L, change in length over length. Okay? Now, we know the length is 4 kilometers. So if we multiply, so we're using, from the graph we get the maximum strain, yeah? We then know that strain is length over extension, so we can work out the maximum increase of length as the strain times the length, which is 4,000 meters. So that's what we got from the graph. Now, is that 0.001 times the diameter of proton? Divide that, what we just calculated, by the mass of the proton, given here, and we get it to be 0.0055, which is to 2 significant figures. Is it? No, it's the same number of decimal places, so it's much greater than the diameter of the proton. That the value given for 0.0 is much greater than I should say, much greater than 0.05 times the diameter of the proton. Yes, I see. Which is greater than the maximal length in the article. Yes? Which is 0.001 times. That's what we're talking about. So the statement doesn't apply. Okay? So there it is. The same equipment. It says the LIGO detector, any change in length of the arms is detected using the interferometer, a laser beam and the photodetector. So the laser beam goes in here, gets split at B, and the split beam goes to mirror X horizontally, mirror Y vertically in the diagram. They then reflect back, and then they're detected here. And if they're in phase, they cause constructive interference, year 12, and if they're out of phase, anti-phase, they'll be creating destructive interference. So it says what I just explained to you here. After reflection, the beams are combined again at B, reach the photodetector, and the photodetector measures the intensity of the light. So if there's a change in the intensity of the light, that means something has caused that. Okay? The system is arranged so the default setting, when no gravitational waves are present, the path difference is half a wavelength between the two split beams that have to travel. So this should lead to destructive interference under default settings. Explain how the photodetector detects very small changes in the length of one arm. So, with no gravitational waves, the path difference is half a wavelength antiphase. So you have destructive interference occurring at the detector. So no signal is the normal with no gravitational waves. A change in one of the lengths of one of the arms will alter the path difference. So there won't be complete destructive interference if one of the paths changes lengths. And there will be some signal will be detected. Because now they're not going to be completely in antiphase. And they don't have to be completely in phase. But if they're not completely antiphase, then they will not destroy each other 100%. One will be bigger than the other. Okay? The system could be arranged, and here's the final part of the exam, the system could be arranged so that when no gravitational waves are present, the beams have zero path difference. That's an alternative way of doing it. So there will be constructive interference at normally, so the default setting could be that there's always some light being produced by the two beams interfering constructively. Explain whether this method, using the initial method of half a wavelength, is more sensitive than using zero path difference method. So the constructive interference, no phase difference, means that you'll have a maximum amplitude signal as your default setting. It will be more difficult to detect a slight change in the intensity of this light from this maximum amplitude than it would be to detect a change from 0. Because if you think about it, the very small change in amplitude from the maximum might not be noticeable so easily, because it will be a very small percentage difference if it's a very small change in length. But the same small change from 0 will be more significant as a percentage change. So it would be less sensitive than the original design in part 2. The way I explained it to my students was, imagine you got a light flickering and it's normally off. You'll notice that suddenly the light appears. But if your light is flickering and all the lights are on, you can't always work out that where the decrease in intensity occurred. Yes, you have to look very closely. So that's a good analogy to use. So I hope you found this run through useful. Here is the final bit that you need to look at while I do my outro instead of the intro to this video. If you found it useful, don't forget to like it, leave a comment, share it, and make sure you're subscribed. And really a positive attitude is what I'm looking for people watching the videos. Remember, I'm doing this in my spare time for you, so you can get access to knowledge beyond lesson times if you're my students. And if you're not my students, I'm just giving it to you for free. So the more likes, shares, and subscribes I get, the more other students get to benefit from my hard work as well. Okay? So thanks for watching, and hopefully see you in a future video. All right? Bye for now.